Okay, welcome to video class number 9, where we are going to study about the Laplace transform. And this is a topic which we have already dealt in S3 and in the subject network theory. We have seen it in very detail. I'll be just brushing these topics, and there is a few concepts which we haven't dealt in S3, and that topic will be emphasized, and all others will be just specified. You may just refer the old notebook as well as the textbook for the details. Okay, now let's start with this. So you have a function. You have a function f of t, as shown here, whose Laplace transform is given as f of s. That is, you can transform a function to another function in S domain, and similarly, if you have f of s, you can have the transformation from S domain to T domain, and this transformation we call as a Laplace transform, and this one is called as the inverse Laplace transform. Now let me tell you the function f of s. How will you evaluate f of s? F of s is nothing but, it is, the first thing is you need to multiply this f of t by what? A function called as e raised to minus st dt integral from minus infinity to plus infinity. So since it is a double-sided function, this Laplace transform is also called as a bilateral Laplace transform. Bilateral Laplace transform. Okay. Now let's have something about S. What is this S? S is defined as, say, sigma plus j omega, right? So that means this is the speciality of this is this one is a complex variable. S is a complex variable. That means this S also represents a complex plane which consists of a sigma part, that's the real part, or you can call like this a real of S in this axis, and this is the imaginary of S, or we call this as j omega axis. Okay, so you have two, sigma axis and j omega axis. So if you are to plot any point of S, you need to plot in this S plane. We call this plane as the S plane, consisting of a real axis sigma and imaginary axis j omega. So this is a complex variable. Now let me just substitute this value of S in this equation. You will get this as integral minus infinity to plus infinity f of t e raised to minus sigma plus j omega into t dt, right? Now this can be written as integral minus infinity to plus infinity f of t into, you can split this exponential as e raised to minus sigma t into e raised to minus j omega t dt. Okay, now you can combine these together, right? Have you ever seen this expression? What is this? This is nothing but it is equivalent in writing integral minus infinity to plus infinity x of t. X of t is f of t into e raised to minus sigma t. F x of t into e raised to minus j omega t. That means this is actually the Fourier transform of what? Fourier transform of a given signal multiplied by e raised to minus sigma t, right? So that's the major relationship between f of s and this is the Fourier transform. F of the Fourier transform, f denotes the Fourier transform, and you can call this as, say, this can be called as the Laplace transform of f of t, or which is defined as f of s. So this is nothing but this is the Fourier transform of f of t into e raised to minus t. So as a statement, Laplace transform is the of a signal, say x of t is what? The Fourier transform of x of t multiplied by e raised to minus sigma t. Okay, hope you understood this. Okay, now the next question is, what is the condition for a signal, for any signal, say x of t, to have its Fourier transform? The condition for any signal, say f of t, to have its Fourier transform is what? This f of t has to be integrable, meaning f of t, when you integrate it from minus infinity to plus infinity, this should not be equal to infinity. That means it should possess a finite value, right? Now, as we did some problems in continuous time Fourier transform, just look at this. This is the problem is again presented before you. Say the signum of t. What is the speciality of signum of t? As I wrote here, this function is not absolutely integrable. So to be precise, or technically, this particular signal is not having any Fourier transform. Fourier transform should not exist for this, but still we managed to find out the Fourier transform of the signum of t. What was the how did we find that? We found out that by multiplying that signal by a limiting function. Now, what do you mean by limiting function? Limiting function is of the form e raised to minus a modulus t, and we know the graph is like this. This is how it goes. So when you multiply any function, any unlimited or non-integrable function by this time limiting function, that gets limited. Okay, so when that gets limited, that becomes an absolutely integrable. Why a signal is not integrable? Because it is not limited in time. It goes on from 0 to, see, look at this. This is actually your signum function. When 0 to infinity, it goes on. It is having a finite value throughout. So when you add this from 0 to infinity, that's going to be infinite. So similar is the case with the next signal which we found out, that is they say Fourier transform of u of t, right? Fourier transform of u of t, that is also not absolutely integrable, that we know that, right? See, look at this. When you add this together, you are not going to get a finite value. So what we did was, we just somewhere or other we made that signal into a in terms of half plus signum of t, right? And then we just substituted the Fourier transform of signum of t by which is being found out by multiplying a time domain by multiplying a limiting function. Now, what is the speciality of this limiting function? See, as you multiply this, the limiting function is represented as e raised to minus a, as a tends to 0. When you put a is equal to 0, this becomes 1. So first of all you multiply, and finally wherever you find a, you will just substitute a to be 0. So that is some sort of so actually what you are doing is, you are multiplying, you are making a non-integrable signal into an integrable signal by multiplying by such limiting function. So similarly, the purpose of, that's what I am going to explain. The purpose of Laplace transform is to get the Fourier. See, if a function is not integrable as per the conditions of Fourier transform does not exist for those signals. Say like u of t, a ramp function. All these signals do not have what? Fourier transform, because they are not time limited. They are not absolutely integrable. So for such classes of signals, we don't have a transform, but at the same time we need to find out its frequency domain. We want to study its frequency component. So in order to study that, we have framed up a transform called as a Laplace transform. So this is basically used for all those signals which are not integrable, where it doesn't have a Fourier transform. So what is the function of this? So as I mentioned, any signal whose the Fourier transform of any, if you want to find out the Laplace transform of any signal, it is nothing but it is the Fourier transform of the signal multiplied by e raised to minus sigma t. So this e raised to minus sigma t acts as what? Acts as the limiting function which we have multiplied in this problem. Hope you get that. Okay, so that is the speciality of e raised to minus sigma t, and the e raised to minus sigma t makes the Laplace transform to act upon non-integrable signals as well. So for those signals which does not have a Fourier transform, you will be having a Laplace transform for those signals. So this is a very important concept that you need to understand. So therefore, from this discussion we can arrive at the condition for a signal to have this Laplace transform. So Laplace transform of a function f of t is nothing but it is the Fourier transform of that f of t multiplied by e raised to minus sigma t. So we know that in order to have the Fourier transform, this signal has to be integrable. So this is the condition for a signal to have a Laplace transform. Therefore the condition for f of t to have its Laplace transform is integral minus infinity to plus infinity f of t e raised to minus sigma t dt has to be less than infinity, or it has to be a finite value. Okay, so we know the speciality of this e raised to minus sigma t. This will make this particular function will make this function a limiting function. Okay, so that's the condition of this sigma t, or in other words you can say that, so you can have this magnitude of this f of t into e raised minus sigma t dt is less than infinity. So from this you can say that what is basically sigma? Sigma is actually the real axis point. That means what will happen in this case? Say for example, if this function, this is a function, say a function like u of t, which is not time limited. Okay, now if that function if it gets multiplied by this e raised to minus sigma t, it will be always integrable as long as sigma is positive, right? Isn't it? As long as sigma is positive. Now what will happen when sigma is less than a value, less than 0? So this becomes positive. E raised to minus sigma t becomes positive. That means this is no longer a limiting function. Why? Because see what happens. This is the condition. For this condition to accomplish, so I will just move on to the next point. Sigma can be equal to 0, sigma can be greater than 0, sigma can be less than 0, right? Now when sigma is equal to 0, what happens is this integral this will be integral minus infinity f of t dt has to be less than infinity. So the Fourier transform of a signal of any signal which is integrable will lie on this in this axis, right? Because here this is the value where sigma is equal to 0, right? Now which is the region where sigma is greater than 0? Sigma is greater than 0. So this line is actually sigma is equal to 0 line, right? Now which is sigma greater than 0? Which is sigma greater than 0? Sigma is, this is sigma, right? So this is the region where sigma is greater than 0, and this is the region where sigma is. So this is sigma greater than 0, this is sigma less than 0, right? So hope you understood this region. Now for example, if you consider say u of t, we know what is u of t. U of t is a signal like this. This is 1t u of t. What is the specialty of this? This is a unlimited time function, or this is not a time limited function, right? And since it is not a time limited function, this has to be multiplied by a time limiting function called as e raised to minus sigma t. Now when you multiply this e raised to sigma t by u of t, this e raised to minus sigma t has to be a function like this, right? Has to be a function like this, provided sigma is always a positive quantity. Sigma is always a positive quantity. Now what will happen when sigma becomes less than 0? When sigma less than 0, this becomes negative. This negative and negative becomes e raised to sigma t. Now what is the specialty of e raised to sigma t? Is it a decreasing function or an increasing function? This e raised to sigma t is something like this. What will happen when you multiply a signal by this signal? That signal becomes a time unlimited signal. So this is it. So that means you need to impose a condition when you find the Laplace transform of u of t, is that this function will be having a Fourier transform only in a certain region where sigma is greater than 0, right? This is the topic which we haven't studied in our history. This region where you have the Laplace transform in an S-plane is called as the ROC, or region of convergence. Okay, so in the case of u of t, if u of t need to have a Fourier transform from this expression, you need to multiply this by e raised to minus sigma t. Now as long as the sigma is positive, that is sigma is positive means this is the region. As long as the S-plane, the sigma is greater than 0, that is the real part of S is greater than 0, you have the Laplace transform of for u of t. That means what happens, what will be the Laplace transform in this region? That is the region where sigma is less than 0. You must say that Laplace transform does not exist in this region. Anyway, this particular signal has got a frequency domain, but that is only existing in the region where the real part of S is greater than 0. So this is a region. Hence, we call this as a region of convergence where the Laplace transform exists. So we call this sigma greater than 0 is the plane we call as the right half plane. Sigma less than 0 is called as the left half plane. So that's it. Now some more about this Fourier transform, Laplace transform f of s. Now f of s can be generally considered as any f of s, that is any s domain function can be generally represented as the ratio of two polynomials of s, right? Okay, now these are also the things which we covered in the last semester. You can equate p of s to 0, that is the numerator to 0, and you can find the roots. Those roots are called as the zeros of the function, while q of s you can equate to 0. Those roots which you get is called as the poles, and the reason also I have explained last semester, that is during this, the zeros, this function will be having a value 0. Q of s, whenever q of s becomes 0, the function extends to either of the poles, so therefore the name zeros and poles. Now basically this function has got a shape because of the zeros and poles. If there would not have been a poles or zeros, it is just a constant function. So this is actually the presence of poles and zeros are said to be the backbone of the Laplace transform function, or in other words, it gives the shape for a function. Then only you will be having some ups and downs in the graphs. Okay, Now let's move on to, after studying the concept of ROC, region of convergence, let's try to do some problems of a Laplace transform. This is the expression that we use for finding out the Laplace transform. Now how to do these problems, all these things which we have dealt in our S3 course and network theory. So but nothing was done for finding out the existence of Laplace transform. We simply use this expression to find out its Laplace transform. Same, but in the signals and systems, you can be asked about the existence of Laplace transform. The existence of Laplace transform will be specified by the region of convergence, which we have just studied. Now the question can be, say you can have some questions. So let's do some problems. Find the Laplace transform of e raised to minus at into u of t, and specify the ROC of the signals. So you must understand that, say, any Fourier transform, for any signal, the Fourier transform the Laplace transform will exist, but it is not necessary that has to exist in the whole S plane. It may be along the imaginary axis, or it may be along the right half plane, or it may be along the left half plane, or both, a combination of left half and right half. We will be doing such problems. So anyway, this is a question. An S3 semester 3 approach is not enough, because in semester 3 we would have just found out this Laplace transform, and we know the Laplace transform of this. This is 1 by s plus a. That was enough in the previous course. But now the question can be asked like this: the ROC, you should specify about the existence of ROC. When you say 1 by s plus a without imposing any condition, that just refers that Laplace transform exists for the whole S plane, but that's not the fact. We should specify in which region of S plane that particular Laplace transform exists. We'll just start as we started the simple problem of Laplace transform. Say x of s is equal to, say, call this as x of t. So what is your x of s? X of s is integral minus infinity to plus infinity e raised to minus at into u of t into e raised to minus st dt. Right. Now in the next step, you can combine this exponential signal, so that you can write this u of t into e raised to minus, you can take outside, plus a into t dt, right? Okay. Now what is u of t? U of t is, we know that u of t is equal to 1 for t greater than or equal to 0. So that means this integral changes from 0 to infinity, 1 into e raised to minus s plus a into t dt. This is the integral we can integrate. Now we know that when you integrate, this is going to be 1 by s plus a. You can do that integration step. That's a very simple. E raised to minus s plus a into t. The integral is e raised to, it will be e raised to minus s plus a into t divided by s plus a. Okay. Now applying the limit from 0 to infinity, you will get this. So you can do that by yourself. It is a simple integration. Now in order to integrate to this value, this particular value, what is the condition? That is s plus a. This is e raised to minus s plus, this is 1 into e raised to minus s plus a into t. If you want to find out the ROC, region where this transform exists, this particular term that comes along with t has to be positive, right? What happens when s plus a becomes negative? This negative and this negative gets cancelled. This is no longer going to be a integrable function. So in order this function to be an integrable function, this real part, right, we are worried about only the real part of s plus a has to be greater than 0, right? That means it has to be positive. Then only this minus will come into action, and this will be treated as a time limiting function. So the important thing is it's time limiting. Now when you combine this together, this has to act as a time limiting function. So in order the signal to have the Laplace transform, this is the condition. What's the meaning of this? Real of s plus a, that is real of s, because a is a constant, so you don't have to specify, it's always real, plus a is greater than 0, or it can be greater than minus a, right? So real of s is greater than a. What is the real of s? Real of s is sigma greater than minus a. Now how will you specify that region? Now the region is, this is the point where sigma is equal to 0, this is sigma greater than 0, and assume that a is positive. Okay, here in the question, assume that a is greater than 0. So as long as a is greater than 0, it is simply a constant. This has to be sigma greater than minus a, meaning it has to start from a negative value. So it is like this, right? And what is the sigma? The sigma has to be minus a. So the sigma has to be greater than minus a, means this is the region. That's why I told you that it can be a mix-up of both right half plane and s plane. So in this problem, it is a mix-up of left half plane and right half plane. So this is sigma greater than minus a. That means this is actually your ROC. This one is called as a ROC, greater than a. Is it clear? Now the next problem is find out the Laplace transform of what? Of minus x of t equals minus e raised to minus at into u of minus t, and specify its ROC. This is a very important thing. It is usually asked in a university question in university. So please, you must understand this very. So what is your x of s? X of s is equal to integral, say minus of, you are taking minus outside, so e raised to minus at into u of minus t into e raised to minus st dt. Okay, so this is from minus infinity to plus infinity. Now first of all, you need to have, what is u of minus t? U of minus t is a signal like this. This is u of minus t, right? So that means this has got signals from minus infinity to 0. So that means you can write this as minus into minus infinity to 0 e raised to minus at into 1 into e raised to minus st dt. Now when you combine this, this will be minus infinity to, no, this is from this is from minus infinity to 0. Okay, so when you combine this, this is e raised to minus of s plus a into t dt. Now this is from minus infinity to, and there is a minus of this. So from the basic course of calculus, you can rewrite this as, so you can interchange this limit, that is to 0 to infinity, but this negative sign goes, this also goes, so that this becomes e raised to s plus a into t dt. Okay, hope you understood this step. That is, this is already a minus and the limit is from minus infinity to 0. We want to interchange that we want to make it 0 to infinity, so that this minus gets plus, this minus also gets plus. So you will have e raised to s plus a into t, or the final result is 1 by s plus, no, this is equal to 1 by s plus a. You can just do the integration part. So okay, it's simple. Now in order to come to this, arrive at this, what is this? So this is positive, s plus a. Here also assume that a is greater than 0. Assume that a is greater than 0. That means this particular, so in order to make this as a time limiting function, this s plus a has to be a negative function. Then only the exponential signal will look like this. Now what about this? As long as it is positive, it will be greater than. So the real part of s plus a has to be less than 0, right? So that is, real part of s is less than minus a, or sigma is less than minus a. So you can draw this region of convergence as what is sigma minus a? Sigma minus a will be coming around here. So this is the plane. Now what is sigma less than minus a? It is the region. Look, so compare these two problems. Here you have e raised to minus 80 into u of t. For such a signal, the ROC is greater than a particular sigma. It is greater than a particular signal. Okay, so it is greater than a real axis. So this is sigma greater than a minus a. Okay, such type of signal. Now coming to this signal, this particular signal is having a ROC less than a particular value, right, in the S plane. This is greater than, this is less than. So that is, this is your ROC of this signal. Okay, so what can you say about the Laplace transform of the signal in this region? You will say that there is no Laplace transform existing in this region. It has got Laplace transform only in the region where sigma is less than minus a. For example, if you are assuming a to be 2, meaning that sigma is less than minus 2. What's the meaning of that? So you have a S plane with sigma is equal to minus 2. That means this particular signal, say minus e raised to minus 2t into u of minus t, will be having an ROC less than minus 2. So this will be in the region. So what about the case where sigma is greater than minus 2? That is the real part of S plane. In this region there is no Laplace transform. Okay, so while we studied in Fourier transform, such type of signals won't be having any, especially this time limiting signal, time unlimited signals will not be having a Fourier transform. But in a Laplace transform, because of the effect of e raised to sigma t, as we studied earlier, that is because of the presence of e raised to minus sigma t, this function can make a signal time limited based on these conditions, sigma greater than 0 or sigma less than 0. Okay. Okay, now the next is another, so the third question here, you are asked to find out the Laplace transform of e raised to minus 3t into u of t plus e raised to minus 2t into u of t. Okay, so this is the signal and specify its ROC. Okay, specify its ROC. You must be very careful. It will be ROC will be a totally different case in this problem. Just a recap. In this problem we have seen one as for a particular signal, it is for sigma greater than a value. In this case sigma is less than a value, and here you have another set of signal. So in this signal, so what we are going to find out is, we will be finding individually the Laplace transform. Okay, what is this property called? This property we have already studied in S3 as well as in the property of Fourier transform. If you have an individual Laplace transform, say call this as x of t, you can find out your x of s will be x1 of s plus x2 of s, right? So you can individually find out so just finding out this. So what is your x1 of s? X1 of s will be integral 0 to infinity. Why? Because of this u of t. So e raised to minus 3t into e raised to minus st dt, right? So this becomes 0 to infinity e raised to minus of s plus 3 t, right, dt. Now what is this? This is exponential e raised to minus of s plus 3 t integral from 0 to infinity, that is upper limit minus lower limit 0 minus of minus 1 by, so this will be 0 minus of e raised to minus 2 by e raised to minus of s plus 3 into t. That means this you will be getting this as minus 1 by s plus 3. Now for this signal to have an Laplace transform, what must be the condition? Here you have already a minus sign. That means this signal, this part has to be always a positive quantity. This should not be a negative quantity, because negative makes this a positive. So this is no longer a time limiting. We want to make this exponential signal always a time limiting function. So in order to have it be decreasing, this must be always a positive quantity. That means this real part of s plus 3 has to be greater than 0, or real part of s, Re of s, has to be greater than minus 3, or sigma for this signal has to be greater than minus 3. Okay, now let's try to do this problem. What is x2 of s? x2 of s is similarly e raised to minus 2t into 0 to infinity. U of t is 1 into e raised to minus st dt, or this is equal to integral 0 to infinity e raised to minus s plus 2 into t. So you can prove this as minus, this as minus 1 by s plus 2, right? Now if you want to write like this, or if this particular thing has to be has to possess a Laplace transform, you need to say that r real part of s plus 2 has to be greater than 0. That is, real part of s has to be greater than 0, or sigma has to be greater than, has to be greater than minus 2, sigma has to be greater than minus 2. Okay, now what is your x of s? X of s is nothing but, it is the combination of this, right? It is the combination of, it is not, okay, here you have plus, here also you have plus. Okay, so you have a negative sign, that makes it positive. This is 1 by, it is not minus, it is 1 by s plus 3, and here also you have 1 by s plus 2. So you can simply, from the linearity property, what is linearity property? It is x1 of, linearity property is x1 of s plus x2 of s. That means you can straight away write s plus 3 plus 1 by s plus 2. But what will be the ROC? You cannot add the ROCs, because this is a region. Now you need to specify the region. Now if you just draw this, what is this region? This region will be from minus 3 onwards, right? And this region will be minus 2 onwards. Now when you combine these two signal, the region has to be the intersection of this region. That means, which will be that? Will it be minus 3? No. Now from minus 3 to minus 2, this particular signal doesn't have a Laplace transform. So when you combine this, this will be having a Laplace transform only in the intersection of this region, and this intersection will be like this. That is from what? From minus 2 to, right? Hope you understood. Okay, so this is, so the, how will you represent this? The sigma has to be greater than minus 2 for this. Okay, this is very important. You shall not write it for sigma greater than, what is wrong in writing sigma greater than minus 3? When you write sigma greater than minus 3, that's valid for this, but that is not valid for this. Now for to be valid for both these terms, you need to have the intersection. Anyway, while you draw, you will understand that the region of intersection will be sigma greater than minus 2. Okay. Okay, now the next question is, that is the fourth, I think. Okay, find the Laplace transform of e raised to minus at into u of t plus e raised to minus bt into u of minus t, where a and b are the positive quantities. Not only that, a is greater than b. A is greater than b. Okay. Now, how to approach this problem? Now it is just as we have done earlier. So you have x of t. So then will you find out x of s? x of s is equal to, I'm straight away doing this. So you can have this signal as minus 0 to infinity. Okay, you can apply the linearity property. So I'm not going to do it individually. So combining this, e raised 0 to infinity, e raised to minus at into e raised to minus st dt, plus here in this example it is u of minus t. So we know that u of minus t exists from minus infinity to 0, 1 into e raised to minus bt into e raised to minus st dt. Now you can combine this together. So this becomes e raised to minus of s plus a into t dt, and this is e raised to minus infinity to 0, e raised to minus of s plus b into t dt. Now you can change the sign by bringing this integral from 0 to infinity. You can sign the change the sign so that this becomes 0 to infinity, 0 to infinity. This will be 0 to infinity e raised to minus s plus a into t dt minus of 0 to infinity e raised to this minus also gets gone. So this will be s plus b into t dt. Okay, now for this signal, so this signal can be written as, so what will be the result of this? This will be what will be this? This will be 1 by s plus a, and this will be when you evaluate that it will be minus 1 by s plus a, that minus and minus this cancel, so this becomes 1 by s plus b. Okay, now the question is, in order to convert this into this expression, this has to converge to a finite value. That is why this region is said to be region of convergence. The integral has to converge to a finite value. So for this integral to converge, or rather for this for the Laplace transform to exist, we know that the real part of s plus a, so here there is a negative sign, so a real part of s plus a has to be greater than 0 in order to retain it as negative. Now here you have s plus b into t. This is a positive quantity. That means this real part of s plus b has to be less than 0 to make it negative. Then only this integral converges to a finite value. So what is the meaning of this? Real part of s is greater than minus a. This is real part of s is less than minus b, or sigma is greater than minus a, sigma is less than minus b. So look at this. So if you want to have this transform to be written like this, as a sum of this should have a common region of convergence. So when you try to draw this, we know that a is greater than b. That is, in the positive direction, this is how it is. That means when you draw it in the negative half, this is minus b and this will be minus a. So for this signal, the region is greater than this region, greater than sigma 1, and for this signal this will be less than this region. Look, so the net region will be a region that lies in between minus a and minus b. So how will you write the sigma of this? This sigma will be a region from minus a to minus b. So this is the region, right? Now let's have a closer look at the problems that we've done so far. Say mark this as problem 1. Okay, this one is, so I'm just drawing this signal. Now just listing these signals. Say first of all we found out e raised to minus at into u of t. What is its Laplace transform? Laplace transform is 1 by s plus a. What is its ROC? ROC is sigma greater than a minus value. That is the first signal. Now let's move on to the second one. Second, we found out e raised to minus at minus of u of minus t. What is its transform? Its Laplace transform is 1 by s plus a, but sigma is less than minus A, right? Now in the third case, that is the third case. Okay, consider this as even though we did another problem of the same type. Okay, now this is the third one. Let's consider this just to make you understand one concept. So the third one is e raised to minus at into u of t plus e raised to minus bt into u of t. So we know that the transform is 1 by s plus a plus 1 by s plus b. But what about sigma? Sigma lies in between minus a and minus b. Now what is the speciality of these three signals? See, this one is a causal signal, right? Only positive going signal, because this is multiplied by u of t. That means this signal is causal in nature. What about this? This is multiplied by u of minus t. This is totally a non-causal signal. Now this is a combination of, this is e raised to minus bt into u of minus t, right? This is a combination of causal and non-causal. That means this is a double-sided signal, right? Double-sided signal. Now if the signal is a causal signal, then the ROC will be greater than a particular value. Sigma will be greater than a, if it is a non-causal value, then it will be less than a particular value. If it is a double-sided, it will be in between two values, the region of convergence. Now where whatever, I mean, you may just do any examples, whatever may be the causal signal will be having an ROC greater than a particular value. Non-causal, purely non-causal, will be having a value less than a particular value, and the double-sided signal will be having a region in between two values. Okay, now another thing to be noted is that is the relevance of ROC. Look at this. This two signal is having the same Laplace transform, but they differ in their ROC. So region of convergence is of immense importance, because we have already proved that two different signals can have the same Laplace transform, but they will be differing in their ROCs. Okay.